Dirk, how are you? La
thank you.
relazione di Dirk
Do you
sarà
hear?
in inglese e quindi ci presenterà dei dati, una specie di meta-analisi sull'editing che lui ed il suo gruppo hanno realizzato negli ultimi mesi. Dirk, thank you very much for being with us.
Thank you.
And the floor is yours. Go ahead.
Thank you. I try to. Do you hear me?
Yes, loud and clear.
Yeah. Okay.
Well, maybe
thank
a little
you
bit
very
more
much,
volume,
and
if possible. It's not possible.
I will
Maybe if you
try.
can increase your volume.
I did
Okay.
so, and I hope that this work. Well, first of all, Roberto and Silvio, thank you very much for this kind invitation. I would have loved to go to Bologna, but although I already bought tickets, I think the COVID situation in Western Europe is actually going worse and worse, and I decided to stay at home, and my presentation will be a little bit different. I will put gene editing in a kind of global perspective, like what we can achieve with it and how the world is looking to gene editing. We have seen already some aspects in this very interesting meeting. Well, first of all, I'm a director from a large institute like in Belgium, but I'm also the coordinator of an international non-profit organization, which is EU SAGE, which represents, in fact, plant scientists from more than 100 European plant science institutes, societies, also academies, and so on. And in fact, all European countries are represented, and we provide information on gene editing for crop improvement, but also we promote the development of European policies that enable the use of genome editing for sustainable agriculture and food production. And if you want to know more about this non-profit organization, which is really is organized by scientists for the society, and in fact, you can look to this website. Now, I think we have seen this afternoon already beautiful examples that how actually gene editing can play a role in our agriculture system. And I think it's clear for everybody that seeds and the starting material, the vegetative propagated crop like grape, like in fact, the quality and the genetic properties of the starting material is extremely important. And only when farmers can use this best material and use their experience and expertise, and in fact we can provide food safety and quality for the consumer. So it's really important that one can start with the best material, for example, disease-resistant material, plants resilient to stress conditions, and so on. And I think it's clear for everybody that maybe with the exception of berries and mushrooms, that almost everything what we eat daily is the product of intense plant breeding. You do not find cauliflower or Brussels sprouts or broccoli in nature. No, you will find still in Europe you can find that a relative brassica, which you would not recognize as being like a cabbage, and this in fact is all been obtained by selection. Similarly, maize, of course, it's the ancestor is a kind of small plant with a few seeds. You can actually not eat. It's a very hard seeds, and that became actually the modern maize. But the same for watermelon, I don't think many people would like the wild banana, which we know now, the Chiquita type of banana, but for example, look to this roots, in fact, which were the ancestor of the carrots. And for every crop, in the thousands of varieties we eat, in fact, you can make similar pictures. And this is actually all these products are obtained by breeding, which is in fact is a process where you introduce genetic information, as we have seen. And there have been a number of milestones in the history of breeding, like, for example, hybrid breeding. We had mutation breeding, mark-assisting breeding. But there is now a new tool since actually less than 10 years, which have been developed. In fact, this genome editing, which is also called precision breeding. Now, if you step back a little bit in breeding, I think we have seen already examples today that this is actually really a problematic process. In fact, it's particularly in view of climate change, where we see that that the changes are very rapid. We see new pathogens appearing, the problems with drought, with too much water sometimes, and so on. And there's really an urgent need to adapt our agriculture to this challenging situation. But the problem, is you rely on luck effect. You rely on genetic changes that occur, in fact, but you have no control on that. So it's actually non-targeted, and it's looking like a needle in a haystack. It's also time-consuming, and we have seen already examples with the grapevines, just in the previous lecture, and it's in some cases it's almost impossible to do that, because if you start to cross species or varieties, you lose characteristics. So in the examples of grapes, you have seen that as well, and I think it's fair to say that this type of approach, which has really been very important for our food production, requires a large investments over many years often. So really a good example is which a disease is called late blight, is called by a fungus, Phytophthora infestans. It's a really devastating fungus when there is a lot of rain and humid periods, and particularly in Western Europe, we have a lot of problems with that. Farmers have now to spray up to 18 times. Well, people have been trying to make resistant potatoes, and the process started in 1960, and it took now 45 years to have actually varieties which are resistant. But these varieties, when you can use them to make soup, but they certainly will not be on your table as a vegetable or to make really what is important for Belgians to make French fries. So this is really a very tedious, very difficult process to do. Unfortunately, there is now this new kit in town. This is precision breeding by gene editing. We have seen beautiful examples, and I'm very impressed by the Italian science in this field, in many different crops. But if you have seen, it is very fast technology. It is the major difference that it is targeted, and it relies on a huge amount of information on the function of genes. One has to realize that the last 40 years, really hundreds of thousands of plant scientists all over the world have been working on understanding plant genomes, how it functions, how they confirm this, how they transmit this information to certain characteristics like disease resistance or fruit quality and so on. So we have this information, and we can now make targeted changes in that information. It's also relatively easy and cheap, and it's accessible to many companies. There are many different forms of genome editing, many very different ways to do it. In fact, so it's also here there is in fact it will be not the same as we have seen before with genetic modification, where only a few companies are really dealing with that, but this will be actually really accessible for many different players. And maybe the most important difference with the classical GMOs is that they are, at least some forms of genome editing is the one which actually we promote, that the plants obtained by this method are indistinguishable from crops developed by conventional breeding. So there's no foreign DNA present there, and that I think makes it actually like a kind of like a breeding product, and therefore the name precision breeding. So the technology, which is amazing, it was only published, in fact, 9 years ago in 2012. It received already in 2020 the Nobel Prize, and as I will show you in a minute, they are already now there are hundreds and hundreds of applications already which have been developed by scientists all over the world, in crops. Now, before I show that, I'm going to just to recall what gene editing can deliver. And we have seen already some examples this afternoon. First of all, I think maybe one of the most interesting application is pathogen and pest-resistant varieties. We want to reduce the use of pesticide in our agriculture. We want to have a more eco-friendly agriculture. And we can do that by genome editing. We can improve nutritional qualities, and that's already been done, like when there's more saturated fatty acid in oils, low gluten wheat, and with all the health benefits. We can improve nutrient use efficiency. For example, the way that plants take up nitrogen, we can make that more efficient so that you have less eutrophication, less leakage of nitrogen in the soil. Resilience to drought and heat, securing our food supplies in climate change condition. Higher yields, in which we maybe can grow the same amount of crops on less land and maybe use the remaining land for reforestation, maybe renaturing actually our landscapes. We can develop protein crops so that we have to rely less on the import of, for example, soybean from the Amazon areas, and we can develop more varieties. For example, since the technology is rather easy to do, one can really think to how to improve old varieties which are not so much used anymore because there are some negative characteristics. How we can improve these old varieties really to, for example, for better flavors, for more colors, for more taste, and we can also think about development of new crops for European agriculture, crops which are not grown here, but which we can adapt, in fact, so that they are more, for example, in terms of reacting to the particular geographic position of Europe, so that they can grow also here and in Europe. Now, you might think, that there are many applications here, but many of them have already been realized in practice. And so we worked with in USH on a database. A database which is not yet published, that will come soon, but a database on gene editing application in crops, so only in crops, not taken into account model plants like Arabidopsis or Marchantia and so on. And we only took into account published information in reviewed science journals. There's actually much more out there. You can certain databases and you can find all that, but this is really a science article dealing with genome editing. And we divided all the application in 7 categories. So improved food feed quality, resistance to pathogens, so biotic stress, abiotic stress, that's high temperatures, drought, for example, improved plant yield, so the yield potential, the post-harvest and the storage. So we have seen examples with aubergine already in this session. Industrial utilization, for example, how to make plants which are better for bioenergy production, and the product flavor and color. Up to date, we have almost 400 records published and taken into consideration that for plant science, it always takes 2, 3, 4 years between the start of an experiment and until the results are published. So this is already, given that the technology is only 9 years ago first being published, this is already a very high number of publication. So where are these applications? Well, you can find them. And here you see in between brackets numbers of publications. The majority of the papers deal with yield, so increased yield, by all kind of methods. It can be increasing the seed number, of the seed size, and sometimes shorter stems so that they have less problems with wind and so on. But there's also approximately the same amount of application in improved feed and food quality. And that's so we're going to show you an example a little bit later. There's also a very large number of applications already in pathogen resistance, or biotic stress, in fact. A number of applications in industrial utilization, and then because it's somewhat more difficult in drought resistance and heat resistance, in abiotic stress, and some in storage performance and the product color, and flavor. So on which plants are now these applications being achieved? In fact, well, it will not surprise you, but a large majority is actually realized in China. China has to feed 1.4 billion people on a relatively limited land space. In fact, and they invest every year approximately 80 billion euros in plant research, in plant and genomics and in genome editing applications. So huge investment. And then, of course, since rice is so important for that land, you see that reflected in also a number of publications. But also here, and that's also in part by Italian scientists, also, by the way, in rice, as we have seen, but tomato, maize, soybean, wheat, potato, canola. You see a number of plants here, including grapevine, in which published work in fact on only a couple of papers, and then you have 43 other actually which have only one paper, the different plants which have only one paper which is really describes an application. So that actually that actually tells you that there is a huge variety of plants that people work on internationally, not just like the classical GMO where we have application mainly in soybean and in maize. No, this is really something totally different what is happening on the global scale. So where are these things happening? Where in the world are these happening? I will give you the next slide here. So most applications originate, and that's not a surprise, given the huge investment into plant research, and most applications come from China, in fact, so 38%. US is also really investing very large in it. Europe is actually not doing that bad. Japan 4%, South Korea 3%, Israel, and then you see a whole range of different countries, in fact, also I'm sure Italy, and also Belgium is part of that, where research is going on, but many of that is still in the process of being published, in fact. So in fact, this is research in crops here, and some of these products already on the market. So some of you might know that the first gene editing crop is marketed in Japan, and this is a tomato which is in fact with health benefits. It lowers actually the blood pressure, and again, it's apparently very popular now to buy this in Japan. This is another one with the health benefits. This is soybean, which a longer shelf life, and which so we can store it for a longer time. It is also obtained by this new breeding technologies. Now, if you look to this situation worldwide, in fact, we have another thing to discuss with you is that, so how is the regulatory status of that? So here in see a world map, it's pretty much updated, where you see that all the countries in green, their genome editing is not regulated as GMO. So people consider this as a kind of new breeding technology, and we will certainly see many of the application coming to the field very soon in many of these countries. So North and South America, Canada, also Australia, Japan, and here there is also in many countries actually the discussion is ongoing, but I'm pretty sure given the investments that, for example, China will very rapidly introduce the technology also for crop improvement, also huge programs going on in Russia and so on. But you see also that unfortunately there are two red areas in the world as being the European Union and New Zealand, and because I think in part due to a completely outdated GMO legislation, it was judged that genome editing would also be considered as GMO, which in effect de facto means that it will be very hard to apply this technology because there is enormous amount of hurdles to overcome, and this is really, I think, really very bad for improving to make our European agriculture more sustainable and more eco-friendly. Fortunately, after this ruling of the European Court of Justice in 2018, there was a very strong reaction by many different partners, including many European scientists, but also the academies, the EFSA, dus the European Food Safety Organization, the there's all kind of farmer organization, consumer organization, and so on. This reaction was so loud that in fact it prompted I would say fortunately the EU Council and to request the EU Commission to make a study on the NGTs. In fact, and that this study in fact was published in a couple of months ago. In fact, and this is now the start to work on a policy proposal for a legislative change, which will most likely be voted by the Parliament in 2023. So there's now a kind of process ongoing, a political process where all the stakeholders will have their stake in discussing this. But given the worldwide efforts in this technology, and given all the possible positive application one can imagine, I really sincerely hope that also Europe, in fact, will allow some forms of genome editing for actually making a better crop for the welfare of our European citizens.
Sorry,
so
Dirk,
in my
to rush you, but we need.
Yes, I will finish two slides
more.
more.
Sorry, and I apologize.
Yeah. No problem. I just want to conclude, in fact, that we believe that this technology is really important to realize the Green Deal, the farm to fork strategy in Europe, by reducing our footprint. And I can think, for example, by using less pesticides. And I think if I can leave one message to all of you, and that we really hope for the future, if the future could whisper, it would call out for CRISPR. And with this, I would like to thank you very much. Grazie, and I will not participate in the discussion afterwards because my Italian is not good enough. But I would, if you have any question or please, you can always address it by email. Thank you very much.
Thank you very much, Dirk. It's been an honor and a pleasure to have you, and we look forward to your visit in May. And remember, a promise is a promise. So we want to see you.
Thank you very much. Thank you. Ciao.
Ciao, Dirk. Very, very nice. Thank you very much. Allora,